morning session. So our first speaker will be Felipe Cano from Universidad of Valladolid, and he'll talk about invariant hypersurfaces for germs of singular holomorphic foliations of codimension 1, the dicritical case. Okay, so Felipe, please.
Thank you, Daniel. Thank you for all of you, and congratulations for this meeting after epidemic season. So I am accompanied by Maria, which is here, Fernando. She says that she's not going to speak very much, so I will speak, but not here. And I am going to start. The title, you can see, is about a very classical problem inside the theory of singular foliations. And the main new contribution to this problem has been done in collaboration with Beatriz Molina Samper. She's there, and you can ask her the difficult questions. So not to me, please. You ask her these questions, and she's going to explain to you the particularities of the work. So I am only going to work about the big ideas on the problem. So this problem, this problem starts with a question of René Tame. The idea of René Tame is that the dynamics given by a foliation, at least in a germified way, should necessarily be organized by a particular solution of analytic nature. So he stated that any germ of codimension 1 foliation in dimension, in general dimension, should have an invariant hypersurface that will be the organizing center in a holonomic way of the dynamics given by the foliation. Like always with Tom, he has a good idea, but not really completely precise. And we are going to speak about the whole history of this problem and some new ideas around the problem. So the question of Tom is, there is a germ. The new question is there a germ of analytic hypersurface invariant for the foliation? I recall briefly that a foliation in an ambient space like Cn is given by an integrable, Frobenius integrable differential one form, and we ask to the kernel of the form that selects at each non-singular point a tangent hyperplane. So an analytic hypersurface is called to be invariant when outside singularities, the tangent space of the hypersurface corresponds to the selected hyperplane given by the foliation. In an analytic way, you can say that the exterior product of the differential form with the differential of the function given the hypersurface is divided, can be divided by the function itself. But geometrically, it is exactly what I am saying. So let us say a few words about the history of this question. The first step in the answer of Tom's question is Camacho-San theorem. So Camacho-San theorem gives a positive answer when the ambient dimension is 2. So the arguments of Camacho-San are based on the classical Seidenberg's reduction of singularities of a holomorphic foliation in C2. Here I have a drawing of what is more or less such a reduction of singularities. It is done only by blowing up points. Each time you blow up a point, you are creating an exceptional divisor that is a projective line. The first blowing up produces a P1, which are the tangent directions at the origin, and you continue and continue, and you have a whole normal crossings divisor. Each of the irreducible components of the divisors, the components of the divisors, are projective lines, because we are working in a simplified case, in a relatively simple case. And the foliation can be transformed, like you transform one form by the pullback. So we have a foliation on the left-hand side and the transformed foliation on the right-hand side, which is the same one outside the exceptional divisor. So if there is one irreducible component of the exceptional divisor that is completely transversal or transversal, generically transversal, but finally, since it is a reduction of singularity, it is completely transversal to the foliation, you can take one of that small curves and you can project that curve to obtain an analytic invariant curve. You can also have corners, but at the corners, when you have done the reduction of singularities, at the corners, there are no more invariant analytic curves or formal analytic curves than the ones given by the divisor. But if you have a singular simple point outside of the corners, there is always another invariant curve which is transversal to the divisor. Unfortunately, sometimes this curve is formal non-convergent one. If you are lucky and this small curve is convergent, you can project it by the blowing ups to obtain an invariant analytic curve. This is the strategy of Camacho and San. So let us continue. So when Camacho and San try to prove this result, they immediately discard the dicritical case. The dicritical case is the existence of one component which is transversal to the transformed foliation, because in this case you obtain in an evident way infinitely many invariant curves. This dicritical case in dimension 2 is evident, and in higher dimension is just the possible obstruction to find an invariant hypersurface. So I will speak about that in a moment. So I am speaking about Camacho and San, they focus on the non-dicritical case. The non-dicritical case means that all the components of the exceptional divisor are invariant for the transform of for the transformed foliation. How they work? They work with something which was known at the time It is the index of foliation with respect to an invariant curve, an invariant non-singular curve. This index is just a residue, and when your singularity is a simple singularity, if the index is non-zero, you can assure that the transversal curve is convergent. This is a consequence of the classical Brio-Bouquet theorem, Brio-Bouquet theorem. So the only thing they have to do is to find, after reduction of singularities, a point which is not a corner and such that the index is non-zero. This assures the existence of a convergent invariant curve that you can project with the reduction of singularities. The first proof is quite complicated, but now the combinatorics inside this control can be done in just one page. You can see, for instance, the proof of Jose Cano around or about these combinatorics. The main properties are the properties which are in this picture. So when you blow up, the index of an invariant curve is the old one minus 1. When you blow up and it is non-dicritical, the sum of the indices is minus 1, which is the self-intersection of the exceptional divisor. And when you are working at a simple singularities, either you have that the product of the indices is 0 or 1. And with all this, you do the combinatory work, and you find your famous invariant curve. There is a version of this theorem of Camacho-San, which is called refined Camacho-San Theorem, which is due to Laura Ortiz Bobadilla and Voronin and Ernesto Rosales, that says more or less the following thing. When you eliminate the critical components, you will find pieces of the exceptional divisor, and in each of that pieces, you are going to find one invariant curve. And you can say even more than that. You can separate the exceptional divisor by what are called nodal separators. I mean, singularities that are real nodes, and in each of the pieces, you also find at least one invariant curve. This is the refined version of Camacho-San theorem. So let us continue. Okay, we are interested in higher dimension. So the first problem we have is that there is no clear result of reduction of singularities when the ambient dimension of the space is bigger or equal than 4. So we need to have a good definition of what is a dicritical foliation. So the definition we are working with, it is inspired in works with Dominique Servault, is the following one. We say that a foliation is dicritical when there is a generically transversal morphism of dimension 2 to dimension n, such that the pullback of the foliation is exactly d of x equal to 0. The image by phi of the axis y equal to 0 is invariant by f. like in the picture. It is like if you are allowed to put a comb, I have no hair, so this thing you use to put your hair in a good way. ¿Cómo se hace peine?
Comb.
Comb. Okay. It is like if you are you have the right of putting a comb in the foliation, like that. This is compatible with the classical definition in dimension 2 of having one dicritical component of the divisor. This could be a piece of this dicritical component of the divisor. And in dimension 3, we have a reduction of singularities. I'm not going to explain too much about that, but I have to do it a little bit. This condition is also equivalent to find a non-invariant component after reduction of singularities in the transformed foliation. Non-invariant component, I mean, of the exceptional divisor. The reduction of singularities should have invariant centers. Okay, so the criticalness is not so easy to define, but in the working problem, you can work like if you have a reduction of singularities with or without a non-invariant irreducible component of the exceptional device. This is the classical Joanolu example. The Joanolu example is an example of foliation in P2 without algebraic invariant curve. But you can see it like a germ of foliation respecting the radial vector field in C3. And this foliation has no invariant surface because it is equivalent to have an algebraic invariant curve in P2 when you blow up. The blowing up, since the foliation is tangent to the radial field, the blowing up of the origin is dicritical. So you have a completely transversal exceptional divisor, and there is no invariant hypersurface. You can do nothing. Well, at the end of the talk, I will say something to say in this case, but it is not possible. So the answer to Tom's question is negative when the foliation is a dicritical foliation, at least in these examples of Joanolu. You can see the written down. It is not easy to remember, but it is circular, and there are many symmetries which help to prove exactly the non-existence of this curve. So the question of the existence of invariant hypersurface now splits into three questions. The first question is to show that any non-dicritical germ of codimension 1 homomorphic foliation has at least one invariant hypersurface. The second question is to find conditions and interesting classes of dicritical foliations that assure the existence of invariant hypersurface. And finally, show that the germs of foliation without invariant hypersurface satisfy certain property of non-transcendence, which is inspired on Brunella's alternative. So I will speak a little bit about these three ideas. The first one is completely solved, but I'm going to give a quick review of how we can solve this first question. The second one, we have some contributions to this second question with Bea, and you have to ask Bea about the technical details. And for the third one, there is some contributions with Mariana Ravara Vago, and I will say in a few moments. So the reduction of singularities in dimension 3 is the tool for proving the existence of invariant surface in the non-dicritical case for foliations in dimension 3. So the statement is more or less like that. There is a composition of blowing ups centered at invariant non-singular subspaces and producing a normal crossing divisor in such a way that any point in the inverse image of the origin is a simple point for the pair transformed foliation and the exceptional divisor. Now the modern language says that you have a foliated space, and a foliated space is your ambient space, a normal crossings divisor, and also the data of the foliation. So you cannot separate the normal crossings divisor of your foliation if you want to work in a coherent way. What we know is that if F is non-dicritical, necessarily all the irreducible components of the exceptional divisor are invariant for the transformed foliation, are non-dicritical components. Okay, this is given by the definition of being dicritical. So let us say a little bit some words about what are simple points in dimension 2 and what are simple points in dimension 3. So in red, I draw the exceptional divisor. It is always an exceptional divisor having normal crossings. In dimension 2, we are speaking about some curves, and we are looking locally at a fixed point. So when we have dimensional type equal to 1, this means that the foliation is non-singular and we have normal crossings with the divisor. So we have two possible type of points which are non-singular. We call corner points to the points which are inside one invariant component of the exceptional divisor. It is possible that there is another one or not, which is a dicritical component. And we call trace points, points which are not contained in an invariant component of the exceptional divisor. And you can have eventually one component which is a dicritical one. The word normal crossings means that you are non singular and the foliation has normal crossings with the divisor. So in particular, you cannot have, in this case, two transversal components of the divisor, because in that situation you have no normal crosses. When the dimensional type is equal to 2, you have a singular point. You have non-nilpotent linear pair without resonant. Resonant is some kind of resonances in order to avoid things which are like the radial situation. And you have two types of points. You have corner points, points in two invariant components of the divisor, and trace points, points in only one component of the divisor. For the trace points, we know that there is exactly one invariant curve transversal to the divisor, that can be a formal or convergent invariant curve. It is always convergent when the index is different of 0. I have already said that. In dimension 3, the simple points are organized essentially in the same way. When the dimensional type is equal to 1, so we have no singular points and normal crosses with the divisor. In this case, you can have two dicritical components of the exceptional divisor because it is compatible with this idea of normal crosses. The dimensional type equal to 2 means that the situation is like an analytic cylinder over a dimensional type 2 simple singularities in an ambient space of dimension 2. So we have a simple singularities in dimension 2, and we have a trivializing non-singular vector field which is tangent to the foliation. So there are also two types of points. There are corner points, inside two components, two invariant components of the exceptional divisor, and trace points that are contained in a single invariant component of the exceptional divisor. In this case of dimensional type 2, it is possible to have one more dicritical component transversal to the trivializing vector field. It is possible. So, dimensional type 3, I'm not going to explain about the analytic definition in terms of equations, but it is like a confluence of points of dimensional type 2. And we have two types: corner points, intersection of three invariant components of the divisor, and trace points, which are points in the intersection of two invariant components of the divisor, and there is a formal convergent invariant surface in such a way that we recover locally the situation of the corner points. There is no more invariant surfaces than the ones which are in the drawing. So there are either 0 or 1 outside the components of the exceptional divisor. Okay, this is very quickly a description of simple points in dimension 3. Of course, there is a work for describing, classifying, analytically, all that, but it is more or less the same situation that you can find in dimension 2. Excuse me, 2, 3, 2. So, what is essentially the argument we have used in collaboration with Dominique Servaux in dimension 3 to prove the existence of an invariant surface? So it is based on what we can call a partial separatrix. A partial separatrix is a maximal connected union of irreducible components of the singular locus of the foliation of trace type. So in the drawing, we have a partial separatrix which has 3 curves. So actually, there is a bijection between partial separatrices and formal invariant surfaces of F, because each of these partial separatrices is like a basis for a germ, which is a closed subspace of the ambient space after reduction of singularities. So by the proper image theorem, the image of all this is in the origin a closed hypersurface. which will be formal when H is formal and convergent when H is convergent. All the details of the are already done. Of course, you can ask to me if this theorem is valid in the formal case. I think it is true. Okay, it is done. So what is the argument? The argument is, if we have a non-dicritical reduction of singularities of our foliation, which is non-dicritical, of course, so there is at least a partial separatrix supporting a convergent invariant surface of F. And how we detect that? So we do a transversal section in dimension 2, and we use Camacho-San theorem to find a convergent curve that we transform by the blowing ups, and this curve will give to us one point in this picture on the partial separatrix. And if this curve is convergent, everybody is convergent in the situation. So this is why we find an invariant surface in the non-dicritical case. In the general non-dicritical case, I mean dimension bigger than 3, you do another thing which is different. We did this result with Mate. You can move a little bit the plane section, but not plane section, the three-dimensional section, and the separatrix you obtain in dimension 3 moves a little bit, and it produces a piece of hypersurface that cohomologically you can apply these results of prolongation, of elimination of singularities, etc. Classical prolongation, results of prolongation. You can do it from 3 to n, but not from 2 to 3, because there is no cohomological triviality for doing that. So this ends completely the non-dicritical case. Assume now that we have dicritical components. So we can speak about this notion of extended partial separatrix. And it is like that. An extended partial separatrix is a finite and maximal connected union of invariant closed curves of trace type. But not necessarily singular. They are closed, and when you are traveling through a dicritical component, maybe your curve is non-singular, but we ask the curve to be a closed curve. And we say that it is complete when each point in a divisor contained there will be inside one curve contained in that divisor. This means that there is no way of losing the invariant hypersurface supported by this extended partial separatrix. So this idea of being complete is important, and essentially we can find a bijection between complete extended partial separatrices and formal invariant surfaces of the foliation working exactly in the same way as in the non-dicritical case. This will be the picture when you find a dicritical component, and you have to travel with a closed curve, etc., and the invariant hypersurface supported by the extended partial separatrix is like in the picture. If we return to Joanolu example, what happened is that the extended partial separatrices are just the curves you have in the picture, and they are not complete because in this part of the dicritical component, you have no possibility of having a closed curve prolonging or continuing the partial separatrice. So you have no complete, but there is another bad possibilities. You can lose also finiteness. This is an example which we are not completely sure with Bea if this example exists in reality. You could ask, for instance, to have a rational first integral on each dicritical component. But the rational first integrals could be not completely integrated one with the other one. For instance, you can travel with one to the other component, and with one to the other component, to the other component, to the other component, and you could produce an infinite processes like in the picture, and this give no an invariant surface. So this situation, of course, exists only when you have two dicritical components intersecting each other. So what is one of the contributions in the dicritical case? The contributions with Bea is in the case of toric type foliations. A foliation is of toric type if you start with coordinates, or if you want a normal crossing divisor with three components, but which are local, your centers of growing up are going to be intersections of irreducible components of the exceptional divisor you obtain each time. It is the same idea of having a very combinatorial kind of reduction of singularities. Excuse me. So by definition, we say that the foliation is of toric type when you can find a reduction of singularities of this combinatorial type. The definition implies the classical Newton non-degenerate condition used, for instance, by Askold, Kovansky, and others. But Newton non-degenerate is a little bit more general. To be precise, Newton non-degenerate should be equivalent to toric type, but asking not simple singularities at the end, but something which is called pre-simple singularities, which is essentially to forget the resonance conditions on the eigenvalues. So it is quite the same thing, but not exactly the same. So toric type foliation may have dicritical components, and each of that dicritical components is a toric surface, and the induced foliation on that dicritical component is of toric type. What is our argument for toric type foliations? So we are making a study inside the dicritical components of a toric type foliation. So we have a foliation of toric type defined in a projective surface, which is a toric surface. Excuse me, I have forgotten to say that S is a toric surface. which is the kind of the critical divisor we find, with associated divisor. The associated divisor D is corresponding to the torus axiom, okay? D inside S. So what essentially Bea has proved is that the prolongation property of isolated branches holds. So this property says that every isolated invariant branch extends to a unique irreducible closed curve, which is necessarily invariant, and moreover, all the branches of Y at the point in the intersection of Y with the divisor are isolated. So with this property, we find complete extended partial separatrices, and hence we obtain an invariant surface for a toric type foliation on C3. So there is one word in this definition we have not defined it, which is an isolated invariant branch. So it is a concept of dimension 2, and this is the definition. An isolated invariant branch is, of course, an invariant branch for a foliation at the point P, and there is a normal crossing divisor which is there. Okay, so we say that the branch is isolated when every infinitely linear point of the branch is singular for G or has no normal crossings with the divisor D or the divisor obtained by blowing up, because an infinitely linear point is a point that is obtained looking at the strict transform of the branch after finitely many blowing ups of points. Intuitively, the non-isolated branches are exactly the branches, the generic branches inside the critical packages. Because if you blow, for instance, one time, you take one of that branches, which are transversal. So at that point, you have normal crossings, non-singular and normal crossings. So this breaks, or this is broken, the definition of isolated branch. And it's exactly what is needed. So with this definition in mind, we can prove the existence of an extended partial separator which is complete. So we find a point like that which is singular. You need to do this exist. And for this, we use Camacho-San Theorem in the refined version. You travel just to a dicritical component, but this gives to you an isolated branch, and it extends and maybe goes to another place, and this branch must be also isolated, and you continue. And in this way, you produce without problems a complete extended partial separatrix, and hence an invariant hypersurface. Another situation when you can do arguments like that is if you have two compact dicritical components never intersect, and there are rational first integrals on the dicritical components. In this case, you can find exactly, more or less in the same way, a complete extended partial separatrix, and hence an invariant surface. This situation, if I remember more or less, I am not completely sure, can occur when your foliation is given by a commutative axiom. What is the other possibility when there is no invariant surface? So the possibility, which is reasonable because philosophically, there is necessarily something which is not completely transcendent. So like that, each leaf contains a germ of analytic curve at the origin. It is exactly what it occurs when you arrive to a dicritical component. The leaves touching the critical components contain a curve which is transversal to the critical component, and you can project that curve. And then all the leaves touching a critical component, say a critical component which is compact in some sense, in the inverse image of the origin, contain a curve like that. But maybe you can have a part of the reduction of singularities where there are no enough critical components to attract all the leaves. This can be true or false. We don't know exactly. We know that there is no attractions like that in particular cases. For instance, when your reduction of singularity is relatively isolated, it is another condition. And this is a joint work also with Mariana Ravara-Bagu. But the general case is not clear. So this is like a conjecture. If you have no invariant surface, this result inspired in Brunella's alternative will hold. So this is essentially the thing I wanted to say to you. So thanks for your attention.
So thank you very much, Felipe. Are there any questions from the audience?
Este aplaudido. Los demás no aplauden ni nada.
Thank you. Nice talk. Okay, so I suppose that well, your Janulus, the Janulus sample